Today we're going to go through a perturbation theory example, right? In previous videos, we've gone through sort of the derivation and what we're doing with perturbation theory. We're going to get some practice and actually look at examples. What we're going to look at today is we're going to look at a harmonic perturbation to our quantum harmonic oscillator. It's nice. This is an exactly solvable problem, which gives us the benefit of, we can approach it using perturbation theory and then solve it exactly and see how well perturbation theory does. So what we're going to do is, consider a quantum harmonic oscillator, uh, which has Hamiltonian just p squared over 2m plus 1/2 m omega squared x squared. And that's our unperturbed Hamiltonian. And then we're going to perturb it with a harmonic perturbation, just some 1/2 m omega squared. Same sort of harmonic potential, but we're going to have, this epsilon here is just some dimensionless number that scales it down. If you want a physical system, I don't know, you can imagine a few of them. Let's imagine you have some semiconductor with some gate voltage, metallic gates on it that are creating sort of a electric potential in the semiconductor that's confining some electrons, say, with a harmonic potential, and then you turn up those voltages and adjust that potential strength and all that and perturb that system. But either way, we have some Hamiltonian that has this, some harmonic oscillator with this potential, and then we perturb it with this one. All right, so in perturbation theory, we're trying to figure out the sort of perturbed energy eigenvalues and energy eigenstates. So how do we do that? Well, first order perturbation theory tells us that the first order correction to those eigenenergies are just the diagonal elements of that perturbation Hamiltonian, right? And we have that perturbation Hamiltonian, so we can do that. Now, in a harmonic oscillator like this, we saw, if we think back to when we covered that, it's often easier to just use, rather than go into position representation and do all the integrals to solve this matrix element, we can just use those operator method, those raising and lowering operators. And if we do that, we know that the X operator can be written in terms of those raising and lowering operators as that, right? So our perturbation Hamiltonian in terms of those operators is just epsilon over 2 m omega squared times h bar 2 m omega times a dagger a squared, right? So simplifying this a bit, we end up with, the m's cancel, so does one of the omegas, and we have epsilon over 4 h bar omega. If we carry this square out, we have a dagger plus a dagger a plus a dagger plus a. And we have our Hamiltonian written in terms of those operators. So if we want to calculate those matrix elements, and 0, h prime, and 0, we can take that Hamiltonian, that perturbation Hamiltonian, and act it on the that nth state. So this is going to be, we can take those constants out. Whoops. And we're just going to operate a dagger a plus a dagger plus a on that nth state. Just going through these, we know, let's go through how each of these operates on n, right? Things we want to remember from when we went through this. The raising operator acting on the nth state gives us square root n plus 1 acting on the n plus 1 state, and the lowering operator on n gives us root n operating on the n minus 1 state. So using those to go through here, this just equals root n plus 1, a dagger acting on n plus 1 state, is equal to n plus 1 root n plus 2 n plus 2 0. The A dagger A state. Just quickly going through these, we're going to get a root n from the lowering operator that brings this to n minus 1. And then the raising operator is going to give us another root n. And we're going to go down and then up and be back at the root n state. Similarly, a dagger n0 is going to give us an n plus 1, a root n plus 1, and bring us to the n plus 1 state, and then another root n plus 1 from the lowering operator, which brings us back down to that n state, and then the lowering operator twice on that gives us a root n and a root n minus 1, and we've dropped down to states in that ladder. So we know how all of these terms in our Hamiltonian are going to act on that state. So we get that first order perturbation to our energy, to our energy eigenvalue. It's just that epsilon over 4 h bar omega n0, and we're going to end up having all of these terms in there, right? We have root n plus 1, root n plus 2 times, let's do these, n plus 2 plus root n times root n is just going to give us n times n0. The n plus 1 squared is just going to give us n plus 1 times n0. And then that last term is root n times root n minus 1, the n minus 2 to the 0th order state. And since these are orthogonal, the only terms that survive are h bar omega times n plus 1. Right? We have this term and this term are the only ones that survive through there. And we get that, and we've sort of figured out what that first order correction is. It can be just simplified to epsilon h bar omega over 2 times n plus 1 half, right? I've just factored out, this is 2n plus 1, factor out the 2, and we get this. So the first order, our energy eigenvalue is just the 0th order plus that first order correction, which is going to be h bar omega n plus, excuse me, 1 half, and that's going to be plus epsilon h bar omega over 2 n plus 1 half. Factoring out the h bar omega, we end up with just h bar omega n plus 1 half. If we factor that out, we end up with 1 plus epsilon. Sorry, epsilon over 2. Right, forgot about this 1 half. So we have our first order correction to our energy eigenvalues. What about the second order corrections, right? So we know that the second order corrections to our energy eigenvalues are sum over m not equal to n, the square of those off diagonal matrix elements of our perturbation Hamiltonian, divided by the difference in energies between the two states that the perturbation Hamiltonian is coupling. Now, we already calculated those matrix elements, right? We had n0 h prime on m. We did this above. This is right here. We calculated those already. So this is equal to epsilon over 4 h bar omega times that n0, and this ended up being root m plus 1, root m plus 2, the m plus 2 state, let's put this in brackets, plus m times the m state plus m plus 1 on the m state. These were the diagonal terms. And then we had that root m minus 1 on the m minus 2 state. So we have those matrix elements. We're looking for when m does not equal m. This whole thing, these matrix elements are just epsilon over 4 h bar omega times, if m not equal to m, we end up with root m plus 1, root m plus 2, delta n m plus 2, and then this off diagonal term, root m minus 1, delta n m minus 2, right? This gives us a delta m n term, but yeah, we're looking for m not equal to m, so these would be 0. So the off diagonal terms that we're going to use in the sum come from here, and we can just sort of do that sum now. We're going to have two terms when m is equal to n plus 2 and when m is equal to n minus 2. So our second order correction to our nth energy state is just going to be, well, this squared, so we have epsilon over 4 h bar omega squared times root m plus 1, root m plus 2 squared, all over e, sorry, these should be n's, e n to the 0 minus e n plus 2, the 0th order correction of that, plus epsilon over 4 h bar omega squared times root m minus 1 squared over e n to the 0. Keep using m. Those should be n's. 0 minus e n minus 2 to the 0. Right? We can simplify this a bit, just, a bit. E over 4 h bar omega squared times n plus 1 times n plus 2. When we square those, we just get rid of the square roots. This denominator, we know our unperturbed energy eigenstates are just h bar omega n plus 1/2. So the difference between n's separated by 2 is just going to be, this tells us that those denominators are both h bar, or 2 times h bar omega. One's positive, one's negative. So this is negative 2 h bar omega because this energy level is 2 h bar omega above that one. And the other one is going to be positive. So this is just n times n minus 1 all over 2 h bar omega. And we can keep going with this and do a little more algebra and simplification. If we, take this square, well, we're going to get epsilon squared h bar omega squared over, this is going to be 16. If we factor out this 1 over 2, this is going to be 32. Factor out that h bar omega in the denominator, these exponents go away. So we have that, take out expand those things, and we get n squared. It's negative because of that in the denominator, negative n squared minus 3n minus 2. On this side, we have plus n squared minus n. So we're doing all this, those cancel. So yeah, and then we have minus 4. So this ends up being epsilon squared h bar omega over 32 times, well, we can bring the negative out, and then we have 2 minus 4n, sorry, plus 4n. We can factor out, let's factor out a 4 out of this, and we get our E, and to our second order correction is going to be negative epsilon over 8, bring up the 4, h bar omega, and then we're left with that n plus 1/2. So our total energy to second order is the 0th order plus that first order correction we calculated above, plus this second order correction. Putting them all together, this is h bar omega n plus 1/2 plus this was, if we go all the way up here, this was this one, which is epsilon h bar omega over 2 n plus 1/2. And this second order correction term is actually minus epsilon squared over 8 h bar omega n plus 1/2. Simplifying this, or sort of just factoring out that h bar omega n plus 1/2, we get 1 plus epsilon over 2 plus epsilon squared over 8. And that is our perturbed energy eigenvalue up to second order using our non-degenerate perturbation theory. Now, that's great. That's a nice result. We can compare this to an exact solution, right? This harmonic perturbation to this system is exactly solvable, right? If we think back, we know our Hamiltonian was h naught plus that perturbation Hamiltonian, which was just p squared over 2m plus 1/2 m omega squared x hat squared, plus that perturbation, which was just epsilon over 2 h bar omega squared x hat squared. We can factor out that x hat squared over 2m plus, and we essentially, when we factor that out, we get 1/2 m omega squared 1 plus epsilon times x hat squared. So we can kind of look at this and just define some omega nu, right? And then this whole thing is just a harmonic oscillator again, p squared over 2m plus 1/2 m omega nu squared x hat squared. And we know, we know the energy eigenvalues for that Hamiltonian are just going to be h bar omega nu times n plus 1/2, right? With omega nu defined as omega times 1 plus epsilon to the 1/2, right? Take the square root of that. So that's well and good. If we expand, if we take this epsilon to be small, right, we know that we can expand that 1 plus 1/2, expanding that is equal to 1 plus 1/2 epsilon, minus 1/8 epsilon squared plus dot, 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 dot. You can do that expansion, and you see here that the exact solved Hamiltonian is h bar omega n plus 1/2, 1 plus 1/2 epsilon minus 1/8 epsilon squared dot, dot, dot. So up to second order in epsilon, it is the exact same solution that we got in perturbation using our perturbation theory. So you can see up to second order perturbation theory works really well. Anyway, that is a quick example working through, stepping back from the whole thing, just taking a Hamiltonian system that we know, perturbing it with some perturbing Hamiltonian, and applying our non-degenerate perturbation theory to figure out the first order and the second order corrections to that. And we showed also that it actually gives us, the exact same solution up to second order um, in that perturbation. If you have questions, bring them up in the synchronous sessions or email me. Hopefully this is starting to all make sense and we're getting used to it. See you later.